Okay, we're starting now. So this is lecture number 6 in our data science for business course. And today we're going to be talking about time series forecasting. Now, time series forecasting is a very well popular and very important process that is used across multiple industries. And just here is just a quick snapshot. What you do is, it's say in logistics and transportation, you try to forecast the volume, for example, of shipped packages, to do the workforce planning, to schedule deliveries. Retail, we talked a lot about retail, and here it's you will forecast of the sales first of all, and demand forecasting. These are the two most important forecasting you can do. Then think about insurance. That's going to be claim prediction. If you think about manufacturing, there are a lot of things you can forecast, and whether it is forecast the breakdowns and forecasting the demand also, and overall the manufacturing process and improve operational efficiency. It's a very big topic in energy and utilities, because forecasting allows you to predict energy load, the demand for electricity demand, and then, of course, that can predict prices, that can predict how much electricity has to be produced, etc., etc. So we'll look a little bit more on the retail side, and here is just an example of real data from sales and the retail store, different groceries. Notice that the sales data is quite oscillatory, right? You do see a lot of fluctuations, and there are different sizes, different volumes, but for example, drops and peaks quite often coincide, and we're going to talk about why and how to deal with that. So when we talk about sales forecast, what do you want to do? Well, you want to predict what's going to be the future sales based on the past sales, on the transactions. Now, the good thing about sales forecast is that you do have sales data, right? And so how much stuff has been sold, and you can use that to model the future. And you can think about this as sort of continuing the sales trend, the way it's shown here on this slide. Now, slightly different task, is actually more complicated task, is demand forecast. And this is trying to predict the demand for certain products in the future. Now, why is it different? Well, because first of all, you don't really know the real demand, right? The sales, how much stuff has been sold. Why is it different? Well, imagine that the store runs out of an item, so demand still exists, but since the item is unavailable, that means sales are saturated, and demand can be much larger than the actual sales. Or you can have multiple items from the same category, and the demand for each item will depend on other items available for sale in that category. Then demand will also depend on all the discounts and other things that the store will run. So demand is harder to predict, but it is extremely important, because demand allows you to, well, first of all, manage relations with supply chain, right? And try to order as much products as needed, right, to satisfy it. It also helps you to manage relationship with the customers, because customers will not be happy if they come to the store and there is no product they're looking for, right? So good demand prediction improves customer satisfaction. Again, it's logistics, it's customer management, it is marketing, because you can actually adjust marketing depending on the demand. If demand may be through the roof, you might not need to spend that much money on the marketing, or if you see the demand is decreasing, you might actually kick in. And of course, within the production, you also need to understand how much stuff you need to produce, right? So this whole supply chain is based on the demand prediction, and the better demand prediction, the more money that the store can make, a retailer can make. You know, for the sort of real world operations, retailers need day level forecasts, and especially if it is groceries, grocery retailers. And remember, groceries are perishable foods, and that means, you know, you cannot store them in stock for a long time. But even with this, with the stuff that you can store in stock for a long time, well, you'll be wasting stock if the demand is low and you order a lot. And so, yes, definitely, you know, demand forecast and demand, you know, the sales and demand curves, they follow each other, but they're different. Now, speaking of demand, again, if you look at this picture, it shows you what happens with demand, you know, depending on, say, promotion or changes in prices, right? There is this notion of price elasticity, or the change of the customer demand depending on the suggested price for the product. And here, it's you can clearly see when the price drops, demand increases. But there are even more subtle things, like, for example, if there's a category of products, and you know, when you do the discount makes the item the lowest price in the category, then demand increases significantly, right? So predicting demand requires to take into account not only sort of the historical behavior of the demand or sales, but also all kind of external factors, right? And those factors could be price changes, and you need to understand how the price change will affect demand. It can be weather forecast, because you know, depending on if it's cold or hot outside, you know, obviously demand, say, for example, for cold drinks or beer will change. Large sporting events, etc., etc. So that all changes demand. And when we talk again about demand, it's usually calculated and predicted on the store level and on sort of daily time resolution, right? And then it can be aggregated for regions. So this is sort of quick introduction into where you use this time series forecast. Now let's talk about the actual techniques, how you do this. So first of all, let's define what is time series forecasting, right? So when we talk about time series is everything, sort of all the data, all the events that we observe sequentially over time. Quite often that data comes with a very particular resolution, and the resolution can be daily, hourly, or if you're talking about, say, some information coming from equipment, it can be seconds or milliseconds. But the thing is, it's usually has equal timestamps. And what we want to do is forecast time series, is try to understand how the time series will continue changing into the future. And here is an example. Blue is sort of the historical data, and yellow is a forecast. So that's what we want to do, right? And you do want in your forecast to have all those peaks and drops that's being learned from the historical data. Now, sometimes if it is only the historical values are available, right? Like, for example, sales and nothing else, well, then your only option is to work with this data, to work with this univariate data, and try to somehow sort of extrapolate it into the future using whatever methods available. But very often there are additional data available, additional features, and then you can formulate this more as a machine learning problem and try to solve it that way. But in any case, we need to have numerical information about the past, about the historical data, and we need to be able to assume that the patterns will continue into the future. Otherwise, forecast is not going to work. And I mean, remember, all forecasts failed when COVID happened because nobody ever seen that. What's going to be? No one's seen that much shutdown and interruption. Or things are happening right now in Russia. You think about try to forecast the exchange rate for ruble. It's almost impossible because it significantly depends on whatever measures the government does. So history might not give you any information about the future of that exchange rate. So here, when you're talking about forecasting, we're assuming that past patterns will continue into the future. So we can learn the past patterns and extrapolate it into the future. Now, there are two methods, two ways to approach time series forecasting. Well, first of all, time series forecasting is extremely important, business task. And of course, there are a lot of statistical techniques, old school classical techniques on how to predict, how to do forecast within time series. First of all, it's based on the patterns, and those patterns based on correlation or autocorrelation, which is the way the signal is correlated with itself, sort of with the values in the past. Quite often, most often, those techniques are univariate, though sometimes multivariate, and can use some external patterns, but it is quite rare in those methods. So, but the bottom line that the method is actually trying to predict the value of the quantity of interest, say it is y at time t+1, based on its values at the previous moments of time, right? Sometimes you try to predict few steps forward. Sometimes it's just the next time step. And there exist a bunch of methods. We're going to touch upon them. Decomposition models that looks into trend and seasonality, sort of classical moving average models, exponential smoothing, ARIMA. We're going to talk about them in a minute. And then there are machine learning methods. And the machine learning methods based on formulating forecasting as supervised learning problem. Now, in order for this to work, you do need to have probably more data points, but you can easily use very many external explanatory factors, and you can handle sort of large data sets. And then the prediction will look like, well, we can train, for example, your function, try to learn the function dependency of explanatory factors on explanatory factors. They're here written as x's, and this is your target variable y. And then, then in the next time step, you can go forward in time, and then you can use, and here it's misprint, you can use again the x values sort of into the future. Or we're going to look into this in more details. You can actually also use those y values themselves within the prediction. And then these are classical algorithms that you can use after that. After you make this formulation, you can use classical regression algorithms, whether it is random forest or gradient boosting decision trees, or sort of whatever you want. All right. So first of all, a little bit about this classical theory about time series decomposition. So when you look at the time series, you realize that often you can decompose it into several components. And there is a traditional names for them. So first of all, it's a trend. And trend is a sort of steady long-term gradual increase or decrease of the values, right? So if you think about your time-dependent data, you might see the trend, say growing trend or decreasing trend, say exchange rate, again, ruble versus dollar. Yeah, it fluctuates significantly, but it has, you know, a trend, increasing trend, with typically ruble was getting weaker against dollar, you know, except for the last 2 months. Seasonality, right? So this is a typically short-term variations that are associated with, say, month or quarters. And think about, you know, sales of you know, summer items versus winter items. You know, if you're talking about you know, warm clothes versus summer clothes, or I don't know, again, beverage sales, ice cream sales, right? They're clearly seasonal. And but seasonal can also be, you know, variations, say on the length of 1 week, right? Where on weekends can be like, you know, larger sales or smaller sales. Now there are also cycles. Now cycles are closely related to seasons, but it is also variations that occur regularly, but they might vary in length. So when we talk about seasonality, we usually have some fixed period, you know, like it's a month, quarters, weeks. When we talk about cycles, cycles can be different in length, and you know, this oscillation node depends on seasons. And then you have some sort of random component, or it's called residual. So if we take the data, remove the trend, seasons, and cycle, well, that's what remains. And those fluctuations are often irregular, sort of random factors, and they're quite often not relevant for prediction, right? And you cannot actually even predict that. So here is the simple example. If you look on the left picture, this is where we see a linear trend, right, in the data. So there's a data, and red line is a linear trend. The trend does not have to be linear; it can be non-linear. But the point is, it's kind of overall slow changing over the entire time frame. Now, this is the picture at the bottom here. These are seasonal effects, right? It's weekly seasonality. This one is newspapers daily sales drops on the weekend, you know, increases during the week. Here's an example of the other cycles. You know, they're not necessarily the intervals not necessarily identical, but that's what we see. And you know, here's a noise signal. Yeah, I see the question, please.
Yes, thank you. My question is about, so here we can see basically 4 time series, right? There are 4 different data sets.
Yes, these are very different data sets. Here is just examples of, you know, what I was trying to, you know, examples clearly showing different sort of cycle versus seasonal versus linear trend. I'll show you on the same data set in a second.
So decomposition does all of that, but with one data.
These are very different data sets. This is again just a simple example.
I see, thank you.
So here is actual decomposition, right? So this is some sort of artificial data set, but imagine that what you have here is, this is what you observe in the data. Let's say this is a data that you have, right? And so you want to decompose it into those components, pull out trend, then do seasonal, then do random. So the way to do this, the simplest way, in fact, you can create a rolling mean, which is you can create a sort of sliding window that replaces all the values by some mean value within this window, and then you move this window through the entire data. And if it's large enough, it will smooth all the oscillations out, and you will get this trend line. Or you could actually, we could try to make it, yeah, we could think about it as a straight line and then just do regression on the straight line. But in fact, here trend is a little bit non-linear, but this is a trend. Then what you do is you subtract from this observation trend, and you do a little bit more of smoothing when you're doing this, and then you'll get this, seasonal oscillations. And then when you take this data and again subtract trend and subtract seasonal, but then you don't do any averaging or smoothing, what's left is those random oscillations. You don't even have them in the observed data. And so this allows us to decompose the data. And in fact, if we see that seasonal oscillations here are very, very periodic and sort of identical, and we assume that that the behavior does not change here, and that's a very important assumption, then we can say that, okay, going forward, seasonal will continue oscillating the same way, and then we have a trend. So this trend is smooth, and we can sort of extrapolate it going forward, growing some way, and adding them back up will give us time series prediction. This is very simple, very straightforward. Now, there are and not very accurate. Of course, there are other ways that allow us to decompose this, or, for example, do decomposition, and then for each of the components, use different methods for prediction, and then add everything up. For those, each of the independent methods, you can actually calculate, the best fit using various techniques. But this is a very good sort of way to understand what's happening in your data, right? And when somebody talks about the trend line, well, that's what it is. Okay, now here is a couple more examples. When you talk about seasonality, there are a couple things could happen. For example, what you see on the left-hand side, this seasonality is additive, which means we take a trend and add seasonality. Now, if you look at the right side, you realize that seasonality is actually, if you go from the left to the right, the amplitude increases, and you can get this increases trend when you have what's called multiplicative trends. So, and I don't know if hold on a second. Yes, okay. And here is at the bottom, I'm just showing you formulas. So in one case, when we do the decomposition, we add things up. In other case, we multiply through. And then if you want to detrend, well, you either subtract this trend that you calculated, or you divide by the trend you calculated, right? And that's called detrending. In general, this classical analysis of time series is based on the idea, based on the notion of correlation in between data points. And in fact, in the case of time series analysis, it's usually autocorrelation. So autocorrelation really means correlation between the values and the lagged values. So the values that are behind. For example, the value at time t+1 will depend on the value at time t, and might depend on time t-1, and might depend on t-2. In fact, quite often when you do this type of modeling, one of the good starting points in your prediction model is just to say, okay, the value at the next time step is equal to the value at the previous time step. Now, to see this correlation, you actually can just plot the values themselves. So on the right axis, we'll take the values at the moment, the time t, and on the x-axis, the values at the moment time t-1, right? So it's a lag of 1. On the left-hand side, you can see actual data. On the right-hand side, you do see this plot color-coded by year, but you realize that there is really a very strong correlation pattern here right? And I mean, you can, well, you can see the almost sort of straight line you can make here as a correlation function. So, you know, on average, if we remove seasonality, right, we'll actually see almost a straight line here, and that's going to be a very easy prediction for the next value based on a couple previous values. So going back to this classical analysis, you know, there are probably three most popular methods, three most popular techniques. The first one is this classical decomposition, and we looked into this, where you consider the time series as overlap or product of several elementary components, which is a trend, cycle, seasonality, and error, and then you can just sort of decompose it into those components. As a formula here, I'm actually showing you a slightly different formula. I'm saying, okay, look, you're talking about seasonality. That means the value at time plus age, for example, is can be looked as a value can be predicted through the value, let's say m steps away, if the period for the seasonality is m. So that's pretty much that decomposition is sort of almost done by hand, right? Now, in other methods, which is very, very popular, is called exponential smoothing method. And this is trying to predict the future value, take into account previous time steps, but making them decay, right? So here it is, alpha was a coefficient alpha. We take the last time step and then 1 minus alpha, the previous 1 minus alpha squared, the one before, et cetera, et cetera. And so you can see easily that this is sort of, you take an exponent and do Fourier, I'm sorry, Taylor expansion, you know, you get this coefficients. And the coefficients alpha, that can be either calculated literally, you know, picked out, and then you check the quality of your prediction, or, you know, you can actually use some sort of combination methods and use machine learning to calculate it. Now, by far the most sort of advanced and widely used method within the classical time series analysis is ARIMA. It's called autoregressive integrated moving average, right? So this is a method that has several components. So one component is autoregressive, and autoregressive, again, it's pretty much the same approach as in exponential smoothing. Autoregression, again, means, you know, it depends on the previous values of the same signal, right? But compared to exponential smoothing, here we have different coefficients in front of the y values. And this is the one part. And the second part is this moving average that actually calculates, within this average, calculates the error, sort of tries to map the error that we create when we do the prediction. And so it's interpolation, interpolation of the previous values of the signal itself plus the reconstruction error. And the coefficients here can be calculated usually through, you know, either least squares or some other approach. There is also extension of this ARIMA model, which is called ARIMAX, where on top of this, you can add dependence on external variables, right? So if there are some external dependencies, you can also do this. You can try to bring this in, but that also makes this ARIMAX method much closer to machine learning, because then you'll need to calculate coefficients for those additional external data point, additional external factors that we bring in. But again, these are very classical statistical methods that were used, for many years before machine learning became very popular. Most of the time, again, these methods are based simply on taking into account the previous value of the signal, the previous value of that variable that you want to predict, right? So again, you think about this as sort of extrapolation of one-dimensional signal, one-dimensional variable. Now, there is one more classical technique that I want to quickly talk about. The reason is it can be used as it can be used, and it is used as a preprocessing for machine learning methods. In order to understand it, we need to touch upon the notion of stationarity of the signal, or stationarity of the time series. And stationarity means that the property of the time series, the property of the signal, does not depend on the time when the signal is observed. So property here means, okay, what's the main value that it doesn't change with time? The variance of the fluctuations does not change, so that the size of fluctuation do not change across time. The autocorrelation does not change across the time. So all the properties of the signal remains the same. And on the left-hand side, you have a stationary time series, and on the right-hand side, it's non-stationary. You see, either those large oscillations, or you see the trend. Now, we already know that we can literally remove this trend, do detrending by calculating it and subtracting it. But in fact, there is a very simple and very, very powerful method that allows us, for most of the time series, to make it stationary. And this is done by differencing. So computing the difference between consecutive observations. That's as simple as that. So instead of calculating and working with the values themselves, we compute and work with the difference, with the deltas at time t and time t minus 1. And then it's also looked as a function of time. Now, typical example of non-stationary time series is, stock price, exchange rates. They're all non-stationary time series, but we can make them stationary by this differencing. Why would you want to do this? Because again, stationarity means that the property of the signal does not change with time, and that makes it much easier to predict. So sometimes when your machine learning model does not work well, does not predict well, what you can do is, for the target variable, instead of predicting the actual value you want to predict, you predict the difference. And then to do the value, you sort of reconstruct the history by adding deltas from sort of day one, or from time point number one. So differencing, again, is an extremely powerful preprocessing technique. So now, if we talk about machine learning methods, well, really, there is just one thing you need to, one idea that you need to capture, and then pretty much all the methods, everything that we have used so far, can be used here too. So how to formulate forecasting in the supervised learning, right? And in particular, since we're predicting numbers, this is going to be a regression problem. Well, one way, we usually do supervised learning is by sort of direct modeling, right? Let's say we have variables x, and we try to predict the value of variable y, and it could be that y is our time series, right? Here it's left to right. Then we can actually just take part of the series and set up a regression model, saying variable y depends on the values of the factors, x1, x2, x3, x4, also at the same moment of time, right? So, at this moment of time, we take x values, we predict the value, y values, it's at next point, we predict y values, etc., etc., etc. Now, if we set up this way, we kind of not using the fact that y is changing with time, and we're completely sort of abstracting from the fact that this is a time series. In fact, and you can also you can only model this when you have all the features, right? When you have those x1, x2, x3. So what do you do if you don't have it? What do you do if you just have the y variables the same way as we discussed so far? Well, the idea is quite simple. What you do is you actually predict y at the moment t plus 1, or t plus h, based on the y at the previous moment of time. So you literally use this variable y both as a feature and as a target variable. So the way to think about this is the following. Let's say you have those time data point 1, 2, 3, 4, 5, and then there's y variables, right? So the way we can convert it into traditional regression problem is the following. For the time step 110, the previous x, the previous value of y is 100. So we use 100 as x, and we use 110 as the one we want to predict. On the third time step, we want to predict this 18 based on the previous value. So previous value goes to x, next value goes to y, and so on and so forth. Yes, we're going to lose, the ends, but so what, right? Where we have a lot of data points. So the idea is, again, this simple. You just take your y values, you shift them, and you look at them you think about them as your x values, and that allows you to formulate supervised learning problem, trying to predict the next values from the previous values. Now, if we do that, then it is extremely easy to actually add to those y values also some other external factors, like those x's. And so then when we look at the regression, we're going to predict the value of y at time, say t, or t plus 1 or t plus whatever we want to, whatever the gap we define. And depending on the y values, so it is sort of allows us to capture all the information usually captured by a Riemann moving average, etc., etc. So get this information of the changing signal with time, but also take and put in external factors if they exist, and if they're function of time, we can put them in, and also if there are some sort of parameters that might not change with time, but we can also put them into the modeling. So this allows us to use sort of all power of traditional machine learning here. And finally, it's quite often that you do not learn and train on the entire sort of data set at once. What you do is you select a window, and it's usually called a sliding window, where you choose to build features, right, within some small window here in yellow, and you predict within the green window. Now you can think about predicting, if this green window is large enough, you can think about predicting at the end of it, or you can say, okay, it's within the window. But or you have a look ahead of size 1, and then you just predict 1 step out, but you train on the data that is here in this colored rectangle. And so the way you generate your matrix for a machine learning problem is you take this window, you calculate features within the window, and again, this can be just explicitly taken values, or it can be whatever features you want to create. You can create features like how many oscillations data had within this window, or what was the mean value, the max value, the variance, the median, sort of anything you want, right? Those used are as X values, and you pick up Y value from this window, and then this gives us one data point in your data set that gives us another data point in the data set, another data point, another data point in the data set, etc. And so you have this move the sliding window through all their training data, and then you learn the mapping from X to Y. And so the value of Y at T plus K, where K is this look ahead interval, right? Based on the function, and this is the values of X, the features, and you can also add not only the feature vector, right, but you can also add the values of the variable Y variable, the one you want to predict. But you take it again, you don't use it sort of all of it, you just take it within this window, within the sliding window. And that allows you to generate the setup for machine learning problem. Now, when you train the model, there is the same standard quality metrics we use for regression we use here. It can be an absolute error, mean squared error, root mean squared error, etc., etc. So pretty much everything that we use, all the mechanics that we use for traditional machine learning is applied here, with one exception, and that exception is extremely important. Your test data should always follow your trained data. Now, when we deal with traditional machine learning, we often randomly sample our data and split it into a train and test set, and that's good. When we do the learning on time-dependent data, it's extremely important that test data go after the trained data. And the reason for that is the test data in the future, trained data in the past. So your past should predict, so your past should not know about the future. If you actually do it sort of other way around, it's usually called signal leakage. So you don't want to use to test on your future, right? I'm sorry, you want to test on your past based on the future. And that makes using traditional cross-validation impossible. So there is a special way you can do cross-validation on time-dependent data, such that those, remember in cross-validation, you can pick out the interval in a data, some intervals from the data, and those intervals can be in different parts of your data set. So here you cannot do it, you shouldn't do it. Again, your testing should always follow your trained data in the time fashion. And so that's where it's extremely important to keep the time steps from earliest to the latest. Okay. But that's really the only difference. The rest of the mechanics just works the same. Now, that was a very quick intro into the forecasting. You know, the topic is large. A couple of books, Forecasting Principle and Practice, and the other one that was called Deep Learning for Time Series Forecasting. It actually, you know, part of the book is dedicated to, you know, classical methods and machine learning methods, and the book is available online, I believe. And of course, again, in this course, we touch on the basic methods, but in fact, the new approaches with deep neural networks, sort of very large neural networks, they work really well on the structured data like computer vision, like text, and for the time series. So there are a lot of successes in using deep learning for time series forecasting. Okay, with that, we are done for today. Any questions, please? Yes.
In any of them, like you showed us several models. Is there a difference in terms of what level of time dimension, let's say, we have? For example, we can have data that is day to day, or hour to hour, or year to year. And we had several examples from, like, we had examples year-to-year data or day-to-day data. And in terms of modeling, are there any restrictions, like which models fit certain data dimensions better?
Okay. No, honestly, this here it's only about the amount of data points you have. So it really doesn't matter whether you have a say 1,000, whether you have a, I don't know, 360, okay, 1,000 days, which is, you know, 3 years, or you have a 1,000 of years data, right? And the data that is sampled once a year, right? So the interval 1 year or 1 day, it really does matter, because, you know, when you put it into, say, either machine learning or traditional schemas, it really does know units, right? It doesn't really care if it is minutes, seconds, years. What really matters is how much of the data you have, and you know, interpretation, right? If you're looking for cycles in the data, then there is sort of corresponding business cycles that are available, right? Yearly cycles, quarterly cycles, etc. But in general, no. Typically, machine learning methods, they require much more data. And if you go into the deep learning, that requires even more data. So if you have only a few data points, it's probably better to just stick with the classical approaches, you know, either ARIMA or you know, moving least squares, or sort of exponential smoothing, sort of one of those techniques.
Thank you.
Any other questions? All right, guys, and on the lab today, we'll be talking about, I believe, sales forecast or demand forecast. I don't remember exactly, but Anwar will tell you. All right, well, that's it for today. Thank you very much. Bye-bye now.
Thank you, goodbye.
Thank you.